We're done. That was nice. L2? What do all the points on L2 look like? 0y. What's my restriction on y? 0 to root 3. And what's f of 0y look like? 0 again. Same exact story. It could potentially be that 0 is my minimum. It could be potentially that my 0 is my maximum. I'll have to check in a second. Now let's move along C1. So C1 is the harder part. So along C1, what do my points look like? Dun, dun, dun.
Is it 1, 4, something?
Okay, so if I come in here and I pick some arbitrary value right there, and I call that x, then how far up am I going to move? So if I call this x, then what's my y coordinate going to be? Yeah, you could basically take this as an equation, solve it for x.
The point wouldn't, well, for that line, wouldn't it be sine t, cosine t, but restricted?
Yeah, but that's if we, yes, we could do that. But now what you're doing is you're reparametizing the curve. We would like to have everything in terms of x because of the derivative we're going to take in a second. So you're turning it into a vector function, which you could still do. But I think it's too much work for us. We don't need it that much. Square root of 3 minus x squared. So, well, you tell me. What coordinate is this? It's the y coordinate, right? So what you're doing is you're trying to solve for the y. So you solve for y here. You move x squared over. You take the square root. I'm only looking at the positive root. Why? I'm on the top half, right? I'm on the top half. Understand? Yes? Now, what's my restriction on x? 0 and root 3. So I have to pick an x that comes from between here and here. All right, now I get the pleasure of plugging that in. So I'm going to plug that into the function. What's f of x root? Ooh, I'm going to get lucky. That is x times y squared. Square that. Oh, nice. That got rid of the root for me, didn't it? Happy. I'm happy. And this is just 3x minus x cubed. Agreed? Now let's find the critical numbers of this. We've never had a cubic, right? We've had a line. We've had a constant. Like along this one, it was constant. We've had a parabola. We've never had a cubic. Well, anything can come out of these. It just depends on your boundary. It depends on your function. You just now need to be able to take the derivative of this. So derivative of f of x root 3 minus x squared is 3 minus 3x squared. And now you're going to set that equal to 0, right? So set equal to 0. And you get x is what? 1 and negative 1?
Yeah.
Right? Plus or minus, but why not negative 1? So you get x plus or minus 1, but because x equals negative 1 does not live inside of, where is it? Here? We throw it out. So, got it? So that means I need to look at a couple of things here. I need to look at, from here, f of, let's do the endpoints. I plug in 0, right, for x. I get 0, and then when I plug in 0 here, I get root 3. I need to look at f of, now let's plug in root 3. So that gives me root 3 what? 0. And then I need to look at the most interesting one, which is x is 1, which means that the y value is what? So just 1 in here, you get root 2. And figure out the values of the function at each of those. How about the first two? 0? right? If I plug in 0 for x, that's gone. Plug in 0 for y, that's gone. So we already knew that, didn't we? We already knew that along these two edges it's 0. So at the corners, or at the two ends of my arc of my circle there, I'm going to be 0. But at that point, 1 root 2, I plug it in and I get what? 2. So can we conclude now? Are we good? We done? You have enough information, you think, now? What's your maximum value? Maximum value is 2. Where does it happen? 1 root 2, 2. Yeah? What's the minimum value? 0. Where does it occur? It's a little more interesting, right? How do you answer that? It answers. Anywhere where you have x 0, you're going to get 0, right? As long as x is between 0 and root 3. And anytime you have 0 for x, and who cares for y, and as long as your y is between 0 and root 3, that's where you're going to get your minimums. So we're saying, that's just how we say along this edge and along this edge. Make sense? Shall we take a look at the picture? All right, let's take a look. Was that a question? No? Okay. There's your domain. There's a domain on the ground. Here's the surface. Weird looking thing. Here's the surface restricted. Okay. And there are the points that we found. Now, I actually did not include, I should include every point on this edge, right? Those are my minimums. Every point on this edge are my minimums. But you can see that part right there. There's our maximum right there. All right? Okay, last one for this section. I think that the page number on that might be wrong. Someone can check on that in a minute. But all right, so let's do a word problem. Find the largest rectangular box with edges parallel to the axes that can be inscribed in an ellipsoid in this ellipsoid. So look at it this way. You have an ellipsoid, right? Here it is. The orangish thing is the ellipsoid. And we want to put a box inside of it. And we want it to be inscribed. When we say inscribed, that means that this point, this point, this point, and this point touch the edge of touch the surface, right? And the bottom edges touch the surface inside. That's what it means to inscribe it. I want to find the largest volume possible. Does this look kind of like a Cal 1 problem? Maybe, maybe not. So look, if I go really tall, what happens? I get a very tall box, right? But it's very narrow. And look, the volume right now is 1.7. I'm having the computer calculate it for me. If I make my y value and my x value bigger, you can see I'm getting a bigger volume, right? 6 now. But if I go too far, if I go too far, what happens is that you're getting more width, but it's shorter. So there's got to be some optimum solution, right? Some optimum. This is an optimization problem. But now we are armed with being able to treat this as a function of 2 variables instead of a function of 1. Okay? Understand geometrically what we're trying to do? Okay, here we go. What are we trying to find the maximum of?
Volume.
Volume, right? We want the maximum volume, which means that you now need to tell me what the equation of the volume would be then. If you're trying to maximize volume, you better be able to express that in terms of some variables. So I'll start you off. V equals. Okay, what is it? X times Y times Z. Let's go back to the picture for a minute. Now remember, we're in three-dimensional space, right? So I have a little thing here that might help us out. Whoa, I don't know if that helped out at all. Why did the other one go away? Okay, look at this point. Can you all see that black point? That's in the first octant, isn't it? That point has the coordinates. You start at the origin, you go out x, right? You go out y, you go up z. That has the coordinates x, y, z. So if you say the volume is x times y times z, it's going to give you the volume of that box. Is that what we're talking about? Is that the box we're talking about? I want one bigger. So I want this point right here to touch the edge of the ellipsoid, right? So what's missing from this? What else do I need? The other 7 octants, exactly. There's another rectangle you need, or another box you need in the second octant, another box you need in the third octant, in the fourth octant, fifth, sixth, seventh, and eighth, right? So I agree with you. X times Y times Z will give you the volume of that box. The volume of the whole thing is 8 of those. So the volume should be 8 X, Y, Z. Agreed? Understand? So that's why I pulled that in there. I took this out. Now, I think if I do that, you can see it. See that? That's just one of the 8 pieces. We agree? Okay, we're trying to find the maximum. I'll leave that. We're trying to find the maximum of this function, aren't we? Its highest value. Right now, this volume function depends on how many things. For us to be able to talk about volume, you must be able to give me x, y, and z, right? Can we find right now the maximum of a function of 3 variables? What have we been doing the last 2 classes? Finding the maximum and minimum of functions of 2, right? So we can't handle this right now, can we? But there's something that we're missing here. This point can't just be any x, y, z. It can't just be anything, right? It must live where? On the ellipsoid, right? This point must also touch the ellipsoid, which means that it must satisfy the equation of the ellipsoid. So let's go back up to the ellipsoid, and let's take a look at that equation, and let's talk about that relationship. I just need, if everyone agrees, I just need to try and convert this into a function of 2 variables, then I'm in business. Yeah? Yeah? Okay. So I would like to get it maybe to a function of just x and y. 2 variables. Can I do it? How? Solve for z. That's it. Look, if that point x, y, z has to live on this, then the x, the y, and z have to satisfy that equation. So solve this equation for z right now. Let's solve it for z. You get 4z squared equals 36 minus 9x squared plus, minus 36y squared. And then divide by 4. Z is 9 minus 9/4 minus 9y squared. I forgot my squared. And then square root. Yeah, I forgot the x squared. That's not going to be a good thing. And so we have square root of 9 minus 9/4 x squared minus 9y squared. Now, it should be plus or minus, right? But we are just going to be looking in the first octant because everything else is just 8 times that. So everyone keep that in mind. What we're doing is we're imagining that we are restricting ourselves to the first octant, aren't we? Restricting ourselves to the first octant? So now just rewrite the volume equation. 8x, y, and yes, this is z. It isn't pretty. Now you can guarantee me that this point lives on the ellipsoid, doesn't it? That point lives on the ellipsoid. It's a function of 2 variables, and I want to know the maximum and minimum values of it. So now my question to you is, am I going to approach this the way we did last class, where I'm going to let the domain be everything? Or am I going to have to look at the maximum of this on a closed-bounded set? What do you think? Closed-bounded? Yeah, because you can't, there are some restrictions on that x, right? That x can't just take off, all the way, just keep on getting bigger and bigger, because you have to live on the ellipsoid. The ellipsoid has some restrictions, doesn't it? So let's see if you can help me get what the domain is. So we're going to be looking on a closed-bounded set. So the domain must be closed-bounded. In 2D. How do I get it?
So that thing is larger than or equal to, well, not equal to.
Solve for, how do you mean solve for y? Okay, so yes, I agree with you, but there's something, let me go back to the picture. Might be a little easier to see. I'll have to erase what I just wrote. What I'm going to do is I'm going to flip this picture over, and we're going to look at it from the top. Okay, let's look at it from the top. Ooh, that's pretty good. Yes? I can change my values of x and y. It's hard to tell. I'm still touching the ellipsoid here, but I am. Right? Do you see that there's, I can let x go from 0 all the way out to some value, right? And y go from here to here, but I can't get to this point, right? I'm not supposed to go there. So my boundary is actually this curve along with this and along with this. Do y'all see that? That's what I need to come up with a, my boundary L1, L2, and C1. Let's talk about L1. If this is the x-axis, this is the y-axis, how would you get this L1? Well, what do you know about those points? They all look like this, right? What's the restriction on x? 0 to something, right? So I heard someone say this. Isn't this picture we're looking at basically taking the entire ellipsoid and smashing it down to the xy plane? So basically letting z be 0, right? If z is 0, I'm just like taking a slice right through the middle of the ellipsoid. So I'd like for us to go to the equation, back up to this, and I'd like for us to let z be 0. If we let z be 0, then we have the rest of what's there is an ellipsoid. Okay, so let's look at that. 9x squared plus 36y squared equals 36. I'll divide everything through by 36. 9 divided by 36 is 1/4 plus y squared equals 1. Now that is definitely an ellipsoid. What is this value right here? What's the biggest it can be?
Is it the square root of 4?
Yeah, so tell me, if I live anywhere on here, right? If I'm on the x-axis, what's my y-coordinate? 0, right? Take that y out of there and solve that for x, and what would you get? It's 2, right? Plus or minus 2. So this is 1, and then the other one's on the other side, but we're not looking at that one. So this is 2, yeah? Now do the same thing over here. This time, x is 0. Plus or minus 1? So this is 1. Understand this? The last thing we need to get, I think from this we can get L1 and L2. All right? We'll be able to talk about those points. What about C1? What do we have to do to get C1? That's right. We know that for C1, I'm going to have a point on here. It's going to have some x coordinate, right? And then the y coordinate is going to be this solved for y, which is the square root of 1 minus a fourth x squared. Move that over, square root. Do y'all feel okay with this? It's a lot to swallow. The fundamental idea is pretty simple, okay? The idea is that if you have a function of two variables and you have some sort of closed bounded set, then all you do is check the inside, check the boundary, compare, and you're done. But those boundaries and setting them up and figuring out what they are can be a little bit involved. All right, let's do this. And I'm not looking forward to setting the partials equal to 0 either. But I have 10 minutes, so I should be able to do it. All right, we all good with that? I'm going to have to erase, but are we all okay with that? Here we go. All right, starting up, now that we have an idea what the domain looks like, start out, first step, I need to set partial of v with respect to x equal to 0. So what's the partial of v with respect to x? Product rule, yay! So what, 8y, square root of a bunch of junk, right? Plus, what's the derivative of the square root of a bunch of junk? 1 over 2 square roots of all that junk, right? Times the derivative of what's inside with respect to x. What's the derivative of what's inside with respect to x? Negative 9 halves x. But then, times, finish your product rule off, 8xy. Okay, remember this, right? So derivative of this with respect to x was 8y times the root. That's this. Derivative of the root of something is 1 over 2 times the root of that something, times derivative of what's inside. Derivative of this, 0, 0, that, bring the 2 down, reduces the fraction to negative 9 halves x, and then finish off product rule 8xy in front. I need to set that equal to 0, folks. All right, so let me clean it up. 8y root junk plus, let's see, this is a 2 down here and a 2 down here, which is a 4. This 4 goes into 8 twice. So I get negative 18, so minus 18 x squared y over root junk equals 0. Can you put these two together? Common denominator, can you? Hope so. Let's see. What happens if I try and put those two together? Well, I have to put this root on the bottom of this one, right? And on the top. And when I put this root on top, the root goes away. So I'm going to have 8y times the junk that was under the root minus 18x squared y all over the common denominator, which was the root of the junk, equals 0. And I think I can go fill the junk in now. All right, let me go fill that junk in. I have to erase. I'm not going to have enough time. 8y, the junk was 9 minus 9/4 x squared. I forgot. minus 9y squared. That was the junk?
Yep.
Double check, yes. Minus 18 x squared y equals 0. Distribute 8y through. And what do we get there? Is everything all right? We good? Okay. What do we get when we distribute that through? 72y minus 18x squared y minus 72y squared minus 18x squared y, where? Y cubed, yes, thank you. Minus 18x squared y equals 0. Any like terms there? These are like terms, right? 72, yes, algebra. Here we are. Hello, haven't seen you in a while. 30, I guess I should write the variable there. Minus 36x squared y equals 0. Divide by what?
Oh, yeah,
36 is a factor of all those. Y'all want to do that first? So 2y minus 2y cubed minus x squared y equals 0. Pull a y out. Then I'm left with a 2 minus 2y squared minus x squared equals 0. My goodness. So y equals 0 is an answer. Right? Y 0 is one possibility. You got to set that equal to 0, right?
Inequality.
How in the world are you going to do that? This is a, what is that? If I set 2 minus 2y squared minus x squared equal to 0, that is an ellipse, isn't it? But let's just save this, because this was only the partial with respect to x. We have another equation to work with, don't we? And we can work with them simultaneously, because we have to solve them both at the same time. So we haven't looked at it yet, but what would the partial with respect to y be?
8x, probably the
Okay, so we're going to run out of time. Would you like to attempt the rest of this for? I hate offering bonus. I'm so buried right now with work. But I'll offer it as a bonus. Okay? Only just so you can, go and try and mess with this. No, let's talk about what you have to do still. You have to do this equal to 0, and you try and solve these two. And if you get an answer that works for both, then you need to make sure it lives in your domain. Right? Make sure it lives inside that original ellipse, which is where we turned it over and looked at it from the side. Then, after you're done with that, you have to move yourself around the boundaries. When you move yourself around the boundaries, L1, L2, and C1, then you got to figure out maxes and mins on that, and then you compare them all. To me, this looks like it's probably the hardest part of the whole thing, is this part. All right, well, oh, I have some stuff for you. Okay, so I have your next mini exam, which is not due until the 23rd of March. That's, I believe, is that the Wednesday after spring break? That's the Wednesday after spring break. You should be able to do everything on this mini exam. I'm sorry, I take that back. You should only be able to do up through 4. Number 4 right now. There's 8 problems. You should only be able to do up through 4. Numbers 5, 6, 7, and 8 all require some stuff from Lagrange multipliers, which is the next section, which I will start on Monday. Remember, Lagrange will not be on the test, So everything we've done up to this point, right here, that's what's going to be on the exam. Cut off right here. All right, so y'all want this now? Yes. And then I have, by request, I have a copy of an old exam that I gave in a Cal 3 class as a midterm. Now, when you look at this, keep in mind this was a summer class, and so their classes were 2 1-hour, 40-minute classes together into one. So they were there for like 3 hours or so. That's how much time they had for this. Your test cannot possibly be this long, but as far as content, you know, this has a good sample of some stuff. I am in no way saying that this is exactly your midterm. I'm just going to go change numbers. But it gives you some idea of the type of thing I gave them, all right? So how about we do this? I'll just put these on a table, and then as you leave, you can just pick them up, okay? Why don't we put them over here? There you go. Everybody have a good rest of your day.